Over the years, the number of known elements has gone up from 37 to 118, making it difficult to study them and their innumerable compounds individually. Hence, scientists started organizing them in a systematic way, such that those with similar properties were placed together and those with dissimilar properties were kept separate. After years of experiments and observations, scientists came up with the concepts of periodic table and periodic law. It classified elements in rows and columns such that the periodicity in their properties, that is, the reappearance of similar properties at regular intervals, could become apparent. A periodic law defines the periodicity in the properties of elements in a periodic table. This classification not only helped scientists in comprehending the properties and chemistry of existing elements, but also in predicting the properties of elements that were yet to be discovered. Since 19th century, scientists have attempted to classify elements using different approaches. For example, in 1817, German scientist Johann Dobereiner noticed similarities in the physical and chemical properties of elements and observed that these elements formed groups of three. He called these groups triads. He found that the elements in each triad, when arranged in the increasing order of their weights, demonstrate that the atomic weight of the middle element is the average of the other two elements. This he called the law of triads. For instance, in the triad of soft, reactive metals, lithium, sodium, and potassium, the atomic weight of sodium, 23, equals the average of the atomic weight of lithium, 7, and potassium, 39. Similarly, calcium, strontium, barium, and chlorine, bromine, iodine also formed triads. However, as Dobereiner's law of triads seemed to work only for a few of the known elements, and hence it was dismissed as mere coincidence. In 1862, A.E.B. Deschamps-Courtois arranged the then known elements in order of increasing atomic weights and made a cylindrical table of elements that displayed the periodic reoccurrence of properties. Deschamps-Courtois' periodic table was important because he was the first person who arranged all the chemical elements in the order of atomic weights. Chemists did not give his discovery its due attention because he used geological rather than chemical terms. Slowly, people recognized the significance of arranging elements based on their atomic weights. In 1865, an English chemist, John Alexander Newlands, propounded the law of octaves. According to the law of octaves, when elements are arranged in the increasing order of their atomic weights, the properties of every eighth element are similar to that of the first element. This trend resembled the octaves in music, wherein every eighth note is similar to the first note. Hence, the name law of octaves. For example, in Newland's periodic table, the 8th element after lithium is sodium, and the 8th element from sodium is potassium. All these elements are similar in their chemical properties. However, Newland's law of octaves was not found to be true for new elements found after calcium. This led the German chemist Lothar Meyer to develop a table of the elements that closely resembles the modern periodic table. He observed a periodically repeating pattern of chemical and physical properties against their atomic weight, while analyzing atomic volume, melting point, and boiling point of elements. Unlike Newland's, Lothar Meyer observed that the length of that repeating pattern was not constant and there was a change in the length, and so created a periodic table based on the increasing atomic weights as given on stage. Unfortunately, his work was published after the work of Dmitri Mendeleev. Hence, Mendeleev is considered the father of the modern periodic table. In 1869, Russian chemist Dmitri Mendeleev published a periodic table and corresponding periodic law of 63 elements known at that time. Mendeleev's periodic law states that the physical and chemical properties of the elements are a periodic function of their atomic weights. Mendeleev created the periodic table by listing the elements in a row in order of atomic weights and starting a new row when the characteristics of the elements began to repeat. This resulted in the arrangement where the elements with similar properties occupied the same vertical column. Mendeleev termed these vertical columns as groups and resultant horizontal rows as series. Mendeleev's success roots to his vision of classifying elements based on the similarities in their empirical formulas and properties of the compounds formed by them. This made him to occasionally ignore the order suggested by atomic weights to classify elements with similar properties together. For example, iodine with lower atomic weight than that of tellurium was placed in group 7 along with fluorine, chlorine and bromine because of its similarities with their properties. Mendeleev also left gaps in the table for undiscovered elements. For example, he left gaps under aluminium, silicon and boron in the periodic table for yet to be discovered elements. He not only predicted the existence of these elements and called them Eka aluminium, Eka silicon and Eka boron respectively, but also described some of their general physical properties. These elements were later discovered and named as gallium, germanium and scandium. Mendeleev's confident predictions and their eventual success made his periodic table win accolades. However, there were certain anomalies in Mendeleev's periodic table. These anomalies were: 1. The position of hydrogen was not correctly defined. 2. There was no place for isotopes of elements in his periodic table. 3. The placement of elements having greater atomic mass before elements having lower atomic mass could not be logically explained. In the early 1900s, discovery of newer elements, isotopes, and the development of atomic theories paved way for the development of the modern periodic table. You have already learned that the anomalies in Mendeleev's periodic table paved way for the development of the modern periodic table. Mendeleev's periodic table was developed at a time when the internal structure of atoms was unknown. Discovery of subatomic particles and their properties took place at the start of 20th century. Isotopes and noble gas elements were also discovered around the same period. These discoveries warranted improvements in Mendeleev's periodic table. In 1913, an English physicist, Henry Moseley, observed regularities in the characteristic X-ray spectra of elements. On plotting the square root of X-ray frequency emitted by elements against their corresponding atomic numbers, Moseley got a straight line graph. However, he did not observe the same pattern when he plotted the same X-ray frequencies against their corresponding atomic weights. Based on his findings, Moseley established that the atomic number, which is the number of protons contained in the nucleus, or the number of electrons surrounding the nucleus in a neutral atom, is a more fundamental property of an element as compared to its atomic mass, as it defines the electronic structure and properties of an element. Hence, Moseley suggested that atomic number and not the atomic mass should be the basis of classification of the elements. Using Moseley's revelation, Mendeleev's periodic law was modified to modern periodic law. According to modern periodic law, the physical and chemical properties of the elements are periodic functions of their atomic numbers. This means that if the elements were arranged in order of their increasing atomic numbers, elements with similar properties would repeat after certain regular intervals. Thus, many anomalies of Mendeleev's table were removed. For example, the confusion about the position of isotopes was solved. Another anomaly, the placement of higher atomic weight elements like tellurium before lower ones like iodine, was also removed. However, the placement of hydrogen was one anomaly of Mendeleev's periodic table that was still not resolved. On the basis of its atomic number, Moseley placed hydrogen at the top left corner of the table without attaching it to any particular group. After Moseley modified the periodic law, several scientists drafted various forms of periodic tables that focused on factors such as chemical reactions, valence, and electronic configurations of elements. Of all these periodic tables, the long form of the periodic table, which is synonymous to the modern periodic table today, is the most convenient and widely used table. It arranges the elements in horizontal rows and vertical columns based on atomic numbers, while keeping electronic configuration as the basis for periodicity in the properties of elements. Similar to Mendeleev's periodic table, in the long form of periodic table, the horizontal rows were called periods and the vertical columns were called groups. The periods contain elements arranged according to their atomic numbers, and the groups contain the elements having similar outer electronic configurations in their atoms. It has a total of 7 periods based on the highest principal quantum number of the elements in that period. Each period contains specific number of elements as suggested by its principal quantum number. For example, first period has 2 elements. Second and third period have 8 elements. Fourth and fifth period have 18 elements. In both the sixth and seventh periods, only 18 elements are shown in the periodic table. Remaining 14 elements of each of these 2 periods are shown in separate panels at the bottom of the table and are referred to as lanthanoids and actinoids respectively. The number of groups total 18 and are numbered from 1 to 18 as per the IUPAC standards. Let's now understand the periodicity of properties in the modern periodic table. As the atomic number increases across the period, the outer electronic configuration changes gradually from one element to another, resulting in a corresponding gradual change in properties of elements. As the atomic number increases, metallic properties decreases and non-metallic properties increases. In a group, all elements have similar electron arrangement and therefore similar physical and chemical properties. For example, all the elements of 13th group in the periodic table have the outer electronic configuration Ns2Np1 and therefore share similar physical and chemical properties. For example, except for boron, all other elements are metallic, are readily found in minerals and ores, and their melting and boiling point decreases as we go down the group. As of July 2009, the long form of periodic table has a total of 118 elements. All the elements between uranium, atomic number 92, and fermium, atomic number 100, are called transuranium elements. The elements after fermium are called transfermium elements. Both transuranium and transfermium elements are man-made elements synthesized in laboratories using costly and sophisticated equipment. Traditionally, newly discovered elements were named either after their synthesizers or discoverers. For example, the element mendelevium, atomic number 101, was named after Dmitry Mendeleev. Similarly, nobelium, atomic number 102, and lawrencium, atomic number 103, were named after famous scientists Alfred Nobel and Ernest O. Lawrence, respectively. However, for the elements with atomic number greater than 103, different groups began to claim credit for the discovery of the same element, causing naming controversies. For example, both American and Soviet scientists claimed credit for discovering element 104. The Americans named it Rutherfordium, whereas Soviets named it Kurchatovium. To avoid such controversies, IUPAC suggested a systematic procedure to be followed for naming elements with atomic numbers greater than 100. They recommended that until the discovery of a new element is proved and its name is officially recognized, an element be named based on a systematic nomenclature. This nomenclature is formulated directly from the atomic number of the elements using the numerical roots for 0 and numbers 1 to 9. The roots are put together in order of digits, which make up the atomic number, with IUM appended to it at the end of the name derived. For example, an element with atomic number 118 should be named as ononctium from 1 is equal to UN, 8 is equal to oct, and IUM. And the first alphabet forms the temporary symbol of the element UUO. After the discovery of the new element is proved, it gets a permanent name and symbol by a vote of IUPAC representatives from each country. The permanent name, thus obtained, might reflect either the name of the country or its state, like germanium, californium, and bohrium. The long form of periodic table is the most widely used modern periodic table. It arranges all the known elements into 7 periods and 18 groups, based on their electronic configuration. Why use electronic configuration to decide arrangement of the elements? To find the answer to this question, let's first review what electronic configuration means. The term electronic configuration refers to the distribution of electrons in the shells and orbitals of an atom. The principal quantum number of a shell, n, defines the energy level of an electron and gives its distance from the nucleus. Shell is further divided into subshells. These are S, P, D, and F. The electronic configuration of an atom defines its physical and chemical properties. For example, as we go from left to right in a period, the atomic size keeps on decreasing. This happens because as the atomic number increases, more electrons get added to the same principal energy level. Due to the same effective distance of electrons from a more positive nucleus due to additional protons, electrons get more strongly attracted to the nucleus, thereby decreasing the atomic size. However, the principal quantum number increases as we go down a group, as the outer shells are more shielded from the nuclear attraction due to additional layer of electrons, and distance from the nucleus as compared to the previous level. This results in increasing atomic size with increase in atomic number. The chemical properties of elements depend on their electronic configuration for the same reason. The elements with higher principal quantum number more readily take part in chemical reactions due to weakly bound outer electron. The chemical reactivity, however, decreases with increase in atomic number for the set of elements having the same principal quantum number. Likewise, the other physical and chemical properties of elements, such as density, boiling and melting points, ionization energy, electron gain enthalpy, and electronegativity, also depend on their electronic configuration. These physical and chemical properties repeat periodically for elements having the same electronic configuration in their outermost shell, a trend that can be seen across the elements belonging to the same group in the long form of periodic table. The long form of periodic table arranges elements with the same principal quantum number n across a period, such that their electronic configuration changes only at the outermost shell. The number of elements in the period, therefore, depends on the maximum number of electrons that principal energy level or shell can accommodate. For example, the first period corresponds to the filling of electrons in the first energy shell or K shell, where n equals 1. Since this energy shell has only one orbital, 1s, it can accept a maximum of 2 electrons. Therefore, the first period has only 2 elements, hydrogen 1s1 and helium 1s2. The second period corresponds to the filling of electrons in the second energy or L shell, where n equals 2. It has a total of 4 orbitals, 1 2s and 3 2p, that can collectively accommodate 8 electrons. The second period starts with lithium with atomic number 3 and electronic configuration 1s2 2s1, ends with neon with atomic number 10. Neon has completely filled p shell and electronic configuration of 1s2 2s2 2p6. The third period corresponds to the filling of electrons in the third energy shell or M shell, where n equals 3. Although this shell has 9 orbitals, 1 3s, 3 3p and 5 3d orbitals, filling electrons in 3d orbitals is not energetically favorable as per Aufbau principle. You will learn more about this principle in the next module. Therefore, only 4 orbitals are available for filling electrons, which allow a maximum of 8 electrons in the outermost shell. As a result, there are 8 elements in the third period, starting from sodium, whose electronic configuration is 3s1, and ending with argon, whose electronic configuration is 3s2 3p6. The fourth period corresponds to the partial filling of electrons in the fourth energy level, where n equals 4. This is because, for this period, filling the 3d orbitals after the 4s orbitals and before the 4p orbitals becomes energetically favorable in accordance with the Aufbau principle. Therefore, this period contains 3d transition series of elements placed after potassium and calcium in the fourth period. The first element in the 3d series, scandium, has an electronic configuration 3d1 4s2. The last element in this series is zinc, having an electronic configuration 3d10 4s2, wherein the 3d orbital is completely filled. The fourth period ends with the element krypton with atomic number 36 and completely filled 4p orbitals. The fifth period corresponds to the filling of electrons in the fifth energy shell, where n equals 5. This period contains 4d transition element series, which starts with yttrium that has an atomic number 39 and ends with cadmium with atomic number 48. The first element in the 4d series, yttrium, has an electronic configuration 4d1 5s2. The last element in this series is cadmium, having an electronic configuration 4d10 5s2, wherein the 4d orbital is completely filled. In the fifth period, electrons enter into the 5s, 4d and 5p orbitals successively. The fifth period ends with xenon with atomic number 54 and completely filled 5p orbitals. The sixth period corresponds to the filling of electrons in the sixth energy shell, where n equals 6. It contains a total of 32 elements and follows the orbital sequence of 6s, 4f, 5d and 6p. This period contains the 4f inner transition series of elements after cesium and barium, also called the lanthanoid series. The lanthanoid series starts at cerium and ends at lutetium. The seventh period consists of most of the man-made radioactive elements that have 7s, 5f, 6d and 7p orbitals filled. This period also contains 32 elements, including the 5f inner transition series called the actinoid series. The actinoid series starts at thorium and ends at lawrencium. It may be interesting to note that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. For example, in the first period, only one atomic orbital is filled, hence the number of elements is 2. In the second and third periods, 4 atomic orbitals can be filled, therefore the number of elements is 8. In the fourth and fifth periods, 9 orbitals can be filled, hence the number of elements is 18. And in the sixth and seventh periods, 16 orbitals can be filled, and hence the number of elements is 32. The classification of elements across periods results in vertical columns of elements that have similar outer electronic configuration, same number of valence electrons, and therefore similar properties. In other words, they belong to the same family or group. For example, all the elements in group 1 of the periodic table have ns1 valence shell electronic configuration. Due to the presence of same number of valence electrons, all elements of this group are alkali metals that show similar properties. The only group that could have distorted this characteristic of all elements in a group having similar properties is group 3, that contains the lanthanoid and actinoid series of elements in periods 6 and 7. To avoid this discrepancy and to maintain the structure of the periodic table, these series are placed separately below the periodic table, thereby preserving the principle of classification. Thus, the long form of periodic table is in perfect accordance with the modern periodic law, keeping electronic configuration, which in turn depends on atomic number, as the basis of classifying elements. We had studied that the position of an element in the periodic table is based on its valence shell electronic configuration, based on the type of atomic orbitals which receive the last electron or differentiating electron. These elements are categorized as S, P, D, and F block elements. However, there are two exceptions to this classification. The first exception is helium. Based on its electronic configuration, it should be placed in the S block in the periodic table. But it is placed in the P block with the other group 18 elements. This is because, like other group 18 elements, helium has a completely filled valence shell and as a result exhibits characteristic properties of other noble gases. The other exception is hydrogen, which has only one electron in the s orbital, and therefore can be placed in group 1 with other alkali metals. However, hydrogen can also gain an electron to achieve the nearest noble gas configuration of helium, and hence can be placed along with halogens in group 17. Therefore, it is considered as a special case and is placed separately on the top of the periodic table. Let's now learn about the S block elements. The S block of the periodic table consists of elements that have the last electron entering the ns orbital. The alkali metals in group 1 and the alkaline earth metals in group 2 of the long form of the periodic table belong to this category. These are soft metals with low melting and boiling points. With the valence shell electronic configuration of ns1 and ns2 respectively, these elements have extremely low ionization enthalpies. That is, they easily lose their outermost electrons to form unipositive ions in the case of alkali metals, or dipositive ions in the case of alkaline earth metals. Therefore, the compounds formed by the S block elements, with the exception of those formed by lithium and beryllium, are ionic in nature. Due to low ionization enthalpies, S block elements are highly reactive and therefore are never found in pure form in nature. They always occur in combined form in nature. For example, magnesium occurs in the combined state as carbonates, sulfates, chlorides, and silicates, but never as pure magnesium. The metallic character and chemical reactivity of S block elements increases as we go down the group. Now let's discuss the properties of the P block elements. The elements of group 13 to 18, situated at the right side in the long form of periodic table, belong to this block. The P block elements, together with the S block elements, are called the representative elements or main group elements. The P block elements have their last electron entering the p orbital. This results in an outermost electronic configuration varying from ns2 np1 to ns2 np6 in each period. At the end of each period is a noble gas element with a stable configuration of ns2 np6. The P block consists of metals, nonmetals, and metalloids. The non-metallic character increases across a period and the metallic character increases as we go down the group. The p-block elements form compounds by loss or gain of electrons, or by sharing the valence electrons. That is, they form both ionic as well as covalent bonds. Two chemically important groups of p-block elements are group 16, the chalcogens, and group 17, the halogens. The elements of these two groups have high negative gain enthalpies, and they readily gain one or two electrons to attain the stable noble gas electronic configuration, which is Ns2np6. For example, chlorine, belonging to the halogen family, readily accepts one electron to attain the nearest inert gas configuration of argon. On the other hand, oxygen belonging to the chalcogen family needs to accept two electrons to attain the inert gas configuration of neon. The group 18 elements having the electronic configuration Ns2np6 are called the noble or inert gases. All of them exist as monoatomic gases. Noble gases exhibit very low chemical reactivity because of their completely filled outermost shell.